Here we are, lecture 24. In this lecture, we will continue to talk about our final analytical chemistry technique of the semester, chromatography. In this technique, we take a mixture of two or more chemicals and flow them through some column known as a chromatography column to separate the chemicals out. And from there, we can start to answer our two major questions of analytical chemistry: what do we have and how much? Although we haven't really gotten into that aspect of things, but we will soon enough. So far, we've just been covering the fundamentals behind this idea. So once again, we have a mixture in a column, and we flow the mixture through the column by using some type of carrier, like a solvent. And we just have that solvent flowing through and pulling these solutes along with it. And we call that carrier species the mobile phase. In the meantime, the column itself has some stationary phase, and right now the type of stationary phase that we've discussed is just having a bunch of particles packed into this column that are going to slow the solutes down as they flow through the column. However, we've already discussed that some solute chemicals will interact with these stationary particles more than other solute molecules that are going through the column. And so the more that the solute interacts with these stationary particles, the slower it's going to travel through this column. And that's going to allow for our chemicals to start separating from one another as some travel through the column faster than others, because they're not interacting with these stationary particles, or stationary phase, as much. So let's see this technique in action. We have two solutes at the start of our column, one green, and behind that is a red solute band. And we'll start flowing them. And we can see that green is getting out of that column faster than the red. It's not interacting as much. As the green particles make it out the column, we can detect them. And as the red particles make it out the column, we detect them at a later time. Now let's talk more about these peaks. Ideally in chromatography, our peak is symmetric and has a Gaussian shape, as it's called. And what this peak represents is really just how many particles are exiting the column and being detected at any given time. So when the peak first starts to form, that represents the first molecule, the first solute molecule exiting and being detected. And then more follow, and then more and more and more until we reach some maximum where we're getting more of those particles coming out the column than at any other time. Then the peak starts to decrease because fewer and fewer particles are making it out, and when the peak ends, that represents the last molecule exiting and being detected of that chemical species. Now, what can we learn from a peak like this? Well, first let's focus on the retention time. This is the time of the peak maximum, and it can be used to identify our solute particles. Because in principle, different chemicals come out at different times, and by measuring the time that they're coming out, we can identify what they are. We'll get more into how we do that in a future video. Next, the area of a peak gives us an idea of how many molecules there must have been, which in turn can be related to quantifying that particular chemical in the overall mixture. Again, we'll get into how we do this in a later video. But the area, of course, is going to relate to both height and width. And so in previous videos, we already covered why the peak has a width to begin with. In other words, why a band of the same type of chemical would still spread out and some of those particles come out sooner than others. And we're going to get way more into that later. But for now, I want to remind you that the typical way that we measured the width of a peak is not the overall width from beginning to end, which is rather difficult to measure accurately, but the width halfway up to the maximum. We can just call this the half width, or to be more specific, sometimes you'll hear it referred to as the full width half maximum. But I won't use that term in this class, I'll just call it the half width. And we want this half width to be narrow because that causes our chromatograms to be less convoluted. And this brings us to a new concept, resolution. So let's write that word down. Resolution. So what is resolution? What does that term mean to you?
It's that thing that I break every year on January 3rd.
I just can't anymore. When I hear the term resolution, I think of picture quality, which is far more relevant to what we're talking about right now. Just look at these two pictures of the movie Spirited Away. Here's one. Here's the other. What are the differences? The image is the same, but the text is in a different location, the color scheme's a little bit different, but the most glaring difference is the picture quality, right? Good, bad, or we could say high resolution, low resolution, right? In the high resolution picture, we can make out the details so much clearly. Even if we zoom in, it still looks good. Whereas if we zoom in on the low resolution picture, we can see how blocky it is because all of these finer details are being merged into this one bigger pixel, and we just can't make out the distinctions between hair and skin very clearly. Resolution in chromatography has a very similar meaning. How well can we distinguish between different chemicals? Are they clearly apart from one another, or are they overlapping and giving a convoluted mess? So we want a high resolution, a good distinction, which requires our peaks be more separate from one another, which has to do with how spread out they are. So let's write this. Resolution, specifically of neighboring peaks, which are most likely to overlap. And it has a simple formula. It's equal to 0.589 times the difference in retention times, delta T subscript R, over the average half width of the two peaks that are neighboring each other. So width 1/2, average. So looking at this formula, we can see that the delta TR represents the difference in retention times. In other words, how far are the peaks away from each other? And the larger that difference is, the greater our resolution. That makes sense, right? The further apart two peaks are, the less chance they have of overlapping. On the other hand, the wider those peaks are on average, the better the chances that they'll start to overlap. So if this number goes up, resolution goes down. We see there's an inverse relationship here. Let's summarize what I'm talking about and then see this in action with an example. So lower resolution, which is bad. It means we can't distinguish things very well. Lower resolution means that there's more overlap of peaks. More overlap of peaks, which could be the result of either the difference in retention times being too small, and there are ways we can fix this issue, although we won't get into them until a much later video, or the half widths might be too large, or particularly the average half width. Or maybe it's a combination of both issues, but the point is either of these can cause our resolution to be poor. And we've already covered one of the major factors that influences the width of a peak, and that was the number of theoretical plates in a column. But I won't review that here. Let's just keep talking about resolution with an example. Imagine we have a two-compound mixture, which we'll just label as compound A and compound B, and that this was run through two different columns of equal length, and in each column the retention time was 40 seconds for compound A and 50 for compound B. The intensity of compound A was twice that of compound B both times. However, the half-widths of each peak were different between the two columns. In the first one, they were 10 and 20 seconds, whereas in the second column, both of those numbers were cut in half to 5 and 10 seconds. Draw a rough sketch of the peaks for each chromatogram and calculate the resolution. So I will do this for the first column in depth to try to make it very clear what's being discussed in this example. So column 1. We recall what a chromatogram's axes are. On the y-axis, we just have this vague word, detector response. In other words, just how many particles is it counting at any given time. On the x-axis, we have time. Okay, And let's just make some tick marks. On the x-axis, let's have 8 evenly spaced markings. So kind of like with the titration curve way back when, we'll start by drawing a mark at the very end. Then we'll cut that in half. And then we'll cut these segments in half. And then cut all of those segments in half. And we'll say that each mark represents an increment of 10 seconds. So I'll label every other one. So 20 seconds, 40 seconds, 60 seconds, and 80. Okay, for the y-axis, I'm not going to bother writing any markings because we're not actually told the heights of the peaks. We're just told that in a relative sense, A has to be twice as tall as B. So here's how we're going to draw this. We'll start with the taller peak, which represents compound A, and we're told that compound A's retention time is 40 seconds. So let's just put a dot at 40 seconds and have it towards the top of our chromatogram. And that represents the maximum of this peak. We're then told that in this first column, the half width is 10 seconds. And since it's symmetrical, we know that this means it spans 5 to the left and 5 to the right. And the span is going to occur halfway up the height of this peak. So right around here, I'm just going to draw this dotted line to represent a span of 10 seconds total. And then I'm going to do my best to draw the peak and connect it to the bottom of the chromatogram like this. Not bad. We can see that the span at half the peak's height is roughly 10 seconds, 5 in each direction. Now I'll go through the same procedure for compound B, whose retention time is 50 seconds, and whose half width is 20 seconds. So at 50 seconds, we will draw a dot that's half as high as the dot for compound A, because we are also told that compound A was twice the intensity of compound B. And so that dot will represent the maximum of compound B's peak, and halfway up to that maximum, we have a span of 20 seconds, 10 in each direction, because again, it should be symmetrical. And so here we go, trying to draw this peak. Something like that, and that. And we can visually see that this is a terrible resolution, right? These two peaks are very much overlapping with each other, and the instrument's not going to be able to distinguish between each chemical. It's just going to measure a total combined signal that looks something like this. It's just a mess. We can't clearly resolve or distinguish one chemical from another. So let me just get rid of that really quick so that I can clear some space for the calculations. To calculate the resolution, we must first calculate the difference in retention times and the average half width, both of which are quite simple to do. So delta TR, well, that's just going to be equal to 50 seconds minus 40 seconds, our two retention times, which is 10 seconds. Our half width average is equal to 10, the half width of peak A, plus 20, the half width of peak B, divided by 2, which equals 15. The unit is still seconds, because both of these widths were measured in terms of seconds. Because the width is ultimately related to the x-axis, which is time. We then calculate resolution by using the formula we wrote down before, 0.589 times our delta TR, which is 10 seconds, over our average half width, which is 15 seconds. Seconds will cancel, and we are left with a unitless number of 0.39. At this point, you should pause the video and try to do column 2 on your own. I will still do it in this video, but since it's a repeat of the same process, I'm just going to fast forward through it, but you can still see me at work. But try it on your own first.
Axes, labels. Blue peak, red peak, calculations.
Okay, so this chromatogram is still not great, but it's clearly better, a lot less convolution, and in turn we have a higher resolution. Notice I didn't bother writing units this time because we already did it on the left side, but you should know what the units are in every case. So the resolution is better, it's still not excellent. For quantitative analysis, we typically want a resolution of at least 2. So let's write that down. I'll write it towards the top. Resolution at least 2, or resolution greater or equal to 2 for quantitative analysis. For quantitative analysis, which we do not have in this case. But we could make it better if we were to increase the number of theoretical plates, because again, that will cause the width to narrow. So far, the only ways we've learned how to do this would be to increase the density of the stationary phase particles or increase the length of the column, since that's also relevant to the number of plates. Okay, I will end this video with the presentation of a clicker, which we will do in Zoom.